for those who weren't there for the first lecture, you can find the lecture notes on my webpage. So last time we introduced marked surfaces, which are topological surfaces closed with boundary and some marked points on the boundary. For instance, this is the two-gon, so this with two marked points. Then we have spanning graphs, which are graphs homotopy to the surface and whose external edges match the number of marked points. For instance, this is a spanning graph of the two-gon. And then we recalled the description of constructible sheaves on such a graph in terms of functors out of the exapath category. Specifically, we're interested in sheaves valued in the infinity category of stable infinity categories. And so, yeah, you just take a functor out of the exit guy, and in this example, this looks like this category. It's always a bipartite poset. And the global sections of such a constructible sheaves then amount simply to the limit of the functor f. And we also recall the description of this limit as coCartesian sections of the Grothendieck construction, which was super important and which will be extremely important for lecture 3. But today you can forget about this if you want. We'll come back to this, so don't erase it from your memory. And what will we do today? So today we will do macro gluing. So last time we had we also discussed this. When you have a gluing context, you have macro gluing of categories, you have macro gluing of objects, and nano gluing of homs. Today we will be doing macro gluing and glue topological Fukaya categories. So somehow, the real representation theories will start in lecture 3 when we start gluing objects. Today we are only gluing categories. And before we can start with that, there's something we need to learn about, which are Kahn extensions. So let's talk about Kahn extensions along fully faithful functors. C0 maps to C is a fully faithful functor. And let's say f is a functor from C to D, where C and D are infinity categories. And there's a definition what it means for this functor to be in the left Kahn extension of its restriction to C0. And the definition is as follows. If you take an object x in the category C, the value of f at x is obtained by the following colimit. This is also known as the pointwise formula for Kahn extension. Pointwise formula for Kahn extensions. And what specifically does this pointwise formula say? So it's kind of a, well, what is this guy? So this is C0 over x. This is the so-called relative slice category. It's defined as this pullback. So its objects are objects of C0 plus a map from the object to x inside of C. For instance, if C0 is equal to C, this would just be the category of, well, this is the usual slice category, but here C0 is a subcategory of C, so it's like a relative version. It's a subcategory of the slice category. And so the condition is that for every object x, your value of the functor at x is given by the colimit over the relative slice category of this functor. So basically, this is the restriction of f to the relative slice category. And this is somewhat abstract, but actually, in simple examples, it's very simple to unravel. So let's say C0 is the span, which includes into the square. So what does it mean for a functor to be the left Kahn extension, so a functor from C to say D? When is it the left Kahn extension of its restriction to C0? This is the case if and only if the value at the additional point star is given by the colimit over the slice category. In this case, the slice category consists of 3 objects, 0, 1, and 2, which each have a unique map to the star. So this thing in this case is the same as C0. So this just means that the value at the star is the push out of F1, F1, F2 over F of 0. Right. And there's another characterization of left Kahn extensions, which we will make use of today multiple times. So let me tell you about this. Theorem. Suppose D has sufficient limits Then there's an adjunction. Between functors from C0 to D and functors from C to D, where this is restriction. So you take the inclusion of C0 into C and you pull back. Restriction. And the left adjoint is left Kahn extension. This is left Kahn extension. And not only do you have such an adjunction like this, which gives left Kahn extension universal property if you want, also this left Kahn extension factor is fully faithful, which is super relevant for a lot of things. And this is only true because the map from C0 to C is an inclusion. If we're looking at arbitrary Kahn extensions, this will be true. Yes, there's a question?
Just out of curiosity, is there a similar statement for right Kahn extensions?
Yeah, absolutely. If you go to the opposite, then yeah.
You might call limits, right? Not limits.
Where? Oh, thank you. Yeah. Other questions? Any other mistakes? Okay, that's good. Then maybe I'll leave these boards on for the meantime while we come back to the actual talk, which will be about these topological Fukaya categories. And so they will come from a. We will introduce a specific class of constructible sheaves on graphs, which for the purposes of these lectures we will call gentle sheaves. I don't think this is an established name for them, but I think it serves its purpose. And their global sections will be called topological Fukaya categories. And they are equivalent to the derived categories of graded gentle algebras. As well as to the partially wrapped Fukaya categories. Of the surface with stops in M. So if you know a little bit about Fukaya categories, they are literally Fukaya categories in some symplectic sense. If you don't, then they are maybe a great gentle algebra for you. And in either case, there will be global sections of sheaves that we will define. And their form is very simple. So what is the idea? A gentle sheaf F assigns. So this is really super basic. It's you take a vertex V of valency n. We want to have that f of v is equal to the derived category of the an minus 1 proper. So the minus 1 here is somewhat important. The a is proper. And if you have an edge E, then the vertex of the gentle sheaf at the edge will simply be perfect. Sorry. All derived categories will be perfect in this talk, and when I forget derived curve, I will. The value at an HE will be the perfect derived category of the field. And then this is the simple idea, and then making this concrete takes at least 1 hour. So what is the problem with this idea, or kind of what do we need to do to kind of whenever you try to study sheaves of categories, there are kind of 2 things you always want to do. The first thing, so typical tasks with sheaves. So maybe 1 is you want to compute the global sections. For example, by a coder. This is kind of what I spoiled already, that the global sections will be graded gentle algebras. We will not discuss this today. Not today, probably not at all in this lecture course. If this was proven by Koncevich. For gentle sheaves. So, right, so typically you will want to compute them. The problem with computing these things, why will we not discuss this today, is because such computations are very hard to do infinity categorically, and the good language to compute with Corvers is model categories and homotopy co-limits, and somehow also discussing that would just be too much material. We're already struggling with infinity stuff, so let's not also worry about model categories.
One quick question.
Yeah.
Will you cover nonetheless the graded case, even if you don't explain why the global sections give you a
Absolutely.
So
absolutely.
not just non-graded gentle?
No, everything. We'll come to the grading later in the talk.
Okay, thank you.
Yeah, I won't explain fully, but there will be some hints of where the grading is hidden. So. Yeah, there are different techniques for how to compute global sections, but typically they involve model categories and homotopy co-limits. And if you're interested, you can ask me about how these arguments work, and I'll be very happy to explain. So today, instead, the focus will be on the second task you typically have when you have a sheaf of categories. Namely, we've chosen one graph on the surface. And then we choose one specific sheaf on that graph. But we are claiming that we're getting the topological Fukaya category of the surface. So you need to prove independence on, first of all, the sheaf, and second of all, the graph. So let's say the gentle sheaf. Of course, if you look at very different sheaves, you will get very different categories. But the point is that there are different sheaves which nevertheless give you the same category. They will be equivalent, as it turns out. And then second of all, if we change the spanning graph, we nevertheless get the same category of global sections. And we'll try to see why that is so, how you prove this. And once you prove these two things, then you're really happy, because then you know that you've kind of chosen a coordinate system, the graph, to compute your category, but you know that the result is independent on the coordinate system you chose, and then you're kind of always free when you want to do a computation to pick a coordinate system, but you don't have to worry about what you're doing to depend on the coordinate system. And so let's call this I, and this double I. So the challenges for I, or challenge for I, which I think this is the main challenge, and this is what we'll focus on starting now, is that if you look at the AN quiver, it doesn't have a rotational symmetry. So the AN-1 quiver obscures, or hides maybe, the rotational symmetry, of the n-gon. Right, we're putting this quiver on the n-gon, and the n-gon you can rotate, and you're not changing the surface when doing that, but it looks as if you're changing the sheaf. And this is not, we'll be able to rectify this. And how do we do this? So, to prove that all gentle sheaves on the ribbon graph are equivalent. We must explain the rotational symmetry of this AN quiver. Okay, so let's start with that. So this will now be on gentle sheaves on the n spider. So essentially this chapter is about representations of the AN-1 quiver. So if you thought you know everything about them, let's see if you learned something new today. Gentle sheaves on the AN spider. So, yeah, about language. So I told you last time that you will have to learn some special language to follow this talk, or you will learn it during the talk. And we will be using some special language now as well because it's somehow more efficient for what we're doing today. So instead of working with the perfect derived category of the AN minus quiver, you can equivalently work with the functor category of, let's do AN. AN is the same as functors out of the n-1 simplex into dperf. This is an equivalence of stable infinity categories. Stable infinity cats. And it does what it does. So an object here representation is a linear sequence of vector spaces, and then you take the derived category of this. And this from the start is a linear sequence of objects and morphisms in the derived category.
Sorry, deeper from what?
K. This is my attempt to draw a K.
Maybe here's the use of the comment that this is another point where we need stable infinity categories or now in some essential way because this statement will be false for triangulated categories. So this is another place where using infinity categories shines.
This is the infinity functor category.
Exactly.
Yeah. Other comments or questions? So concretely, or not concretely, let me say, objects correspond to sequences in the path of the following form. So we will also be, so they are x0, x1, xn minus 1. So if you want, we're just relabeling the AN quiver by labeling the vertices from 0 to n minus 1 instead of the usual way that representation series would do from 1 to n. But it's somewhat cosmetic. This is that, and we're all still getting used to the infinity language, so let's do a warm-up. Warm-up, which is turn the assignment of, so we take a representation like this, and to map it to the fiber of the map from xi to xi plus 1. And as hopefully we've emphasized enough, you cannot define infinity functors on objects. It's not how the theory works. So it's new to the theory. Somehow very unclear. How do you define a functor like this? And let's do this. It's kind of, if you know the theory, it's really elementary, but I think it's good to for everyone to be on the same base with it. So we turn the assignment into an exact infinity functor, which will denote by fiber I plus 1 from the representations of the AN quiver to the 0. And for this, we compose two functors. We compose two functors. So first of all, we look at the inclusion of delta 1, which is delta I plus 1, including delta n minus 1. So this is kind of notation people often use to indicate that this maps these two, the two zero-sum indices. This is 0 goes to 1. This is a map of some special sets, and I map 0 to I and 1 to I plus 1 inside of delta n plus 1. This is an inclusion. Let's call it iota I plus 1. And if we take the pullback, this gives you a functor, iota star, I pi I plus 1 from factors delta n minus 1 to d per of k to factors delta 1 d per. And I'm claiming this factor is an exact factor. Does someone know why it's an exact factor? The hint is on the other board. Yes?
It has a left and a right.
Given by?
Left and right connection.
Exactly, yeah. And so left and factors which have left and right adjoints, they are automatically preserve all limits and colimits which exist. Hence, it's in particular an exact factor since it preserves finite limits and finite colimits. So is exact since left adjoint is left time extension. And this means it preserves, if it has a left adjoint, it preserves limits, and hence it preserves also time.
Can you spell out exactly what the situation was? Was this not like a really general argument, like every restriction into
Yeah, you need the target to have sufficient limits and colimits for the Kahn extensions to exist.
Yes.
And then restriction has adjoint.
Okay. Then restriction along, like I guess.
Let's say fully flipped counter for now. For arbitrary functors, it's similar. But then you may, yeah. So now, if you have sufficient limits, then or colimits, it's somewhat useful. Alright, and the second functor is you take the fiber functor from functors delta 1 d per of k to d per of k. And this is an exact functor, which is one of the maybe cornerstone facts of stable categories. If you want a reference, you can read about this in higher algebra 1.1.1.7 and 1.1.1.8.
It's the same thing as an adjoint.
Well, how do you know that what the adjoint is? How would you ever prove that?
Send an object to the zero-morphism into an object.
Yeah, but how do you prove this? Well,
Like, what is the fiber? That's the real question.
The question
It's a limit.
I mean, as Merlin said, if one is familiar with the theory, it's very elementary to see. But you can, of course, use an argument using Kahn extensions as well.
Yeah, I mean,
we need to write
if you unravel everything from the start, this is somehow where you have to begin.
If you want to do it, it is a right Kahn extension.
That's the question?
Say with the left Kahn extension argument, you have to argue that, right? Because this category is actually not critical.
Well, it has the colimits you need, right? It has finite colimits, and all of these slice categories in that case will be finite.
But also, I mean, colimits are simply computed pointways, right? So it's going to be easier to see it exact.
Yeah, that's another way to that's another way to argue this, if you want to. Yeah. All right. So we have this fiber factor. You can read about in the first chapter of algebra, which is very readable if you want to. And we can compose these. We compose and get fiber I plus 1, which simply defined as fiber composed with delta I plus 1 whole back. Easy exercise, but maybe good to have that. Now, similarly, we need two other functors. Similarly, the assignments. So if you take x0, x1, xn minus 1, and if you want to map this to x0 or to xn minus 1, this is now easier than before. These two assignments again can be turned into factors which are exact. Come from exact functors. Exact functors, which we will label as follows. We have pi 0, which is we take pi. You take delta 0, including delta n minus 1, you simply take the fullback. This is a factor from delta n minus 1, d perf, okay, d perf, okay, and pi n minus 1 is the same fullback along the object n minus 1. So this notation will be recurring during the talks. It's very important to remember. It's fiber I plus 1 and pi 0 pi -1. Question?
In 2, it can be delta 1.
Delta 1 and 2? Yes, this is delta 1. Yeah.
Can you push up for
Yeah. Thanks.
Thank you.
So these functors will be what we put on the sheaf. So definition. Let Gn be n spider, which looks like as follows. So it's the ribbon graph with one vertex and n external edges. N spider. And B is n valent. And then you define Fv from exit of Gn to stable by setting Fv of v to be simply functors from delta n minus 1, no, n minus 2. So at the n valent vertex, we're putting the a n minus 1 cover, which corresponds to the n minus 2 simplex, as we just saw. Okay. We said Fv of the I to be the curve. Okay, and then you define Fv from v to ei simply to be, well, you have 3 cases. It's pi n minus 1 if I is equal to 1. It's fiber n minus I n minus I plus 1 if I is between 2 and n minus 1. And it's pi 0 shifted by 1 if I is equal to n. And we call VF the gentle sheaf on the n spider. We'll get to arbitrary ribbon graphs later. This is somehow our first candidate. And somehow now we run into this problem of having chosen an edge, calling it E1. But what if we choose a different edge and call it E1? Do we get the same sheaf or not? And this is kind of very important to make sense of. Because otherwise we would immediately get stuck trying to make any arguments. So this is a graph. A priori you could imagine it just as n edges and you didn't label them yet. And then you're choosing, they have a cyclic order by it being ribbon graph, but they don't have a total order. By choosing an edge which you call E1, you're saying this is the first edge, this is the second, this is the last. And then you're choosing additional data, and once you've chosen this additional data, you're writing down the sheaf. And if I say this is my first edge and this is my last edge, then I get a different recipe for my sheaf, and it's not clear that they're the same recipe. Yeah, exactly. But the sheaves, if you pull back along this equivalent of exit path categories, the sheaf doesn't get transformed to itself necessarily.
So this precondition to always cyclically invariant.
No, not at all, right? If you rotate, this doesn't look like it becomes itself. We'll kind of clarify how you do this. So, first of all, let me spell this out for n to 3. Maybe it will become slightly clearer. So you can depict the function the sheaf as follows. You have d perf of k. You have fiber 0, 1 going to d perf of k. You have pi 1 d perf of k. And you have pi 0 shifted by 1. Okay. and this maps A goes to B to A shifted by 1. This maps A goes to B to the fiber of alpha, and this maps it to B. This is our diagram in the case n is equal to 3. Right, the graph is this graph. B1, B2, B3. Okay, let's compute the left adjoints of these functors.
So it was pi n minus 2.
Thank you.
Okay.
Yeah. So if you take the left adjoint of the fiber functor, this is, you'll kind of have to trust me what it is. The other two we will be able to compute using Hahn extension. So this is tensoring with this module. So we have okay to functors from delta 1. We have okay. And we will call this guy S0. So this maps K to this guy. And yeah, if you want, it's a simple module of the A2 quiver where we at the vertex 0 because we label the vertices 0 and 1.
In general, V maps. I mean, you can give like a heuristic formula of an object, which is just V goes to V to 0.
Oh yeah, exactly.
B to the 0.
Yeah, absolutely. And then pi 1 left adjoint, and this you can compute using Hahn extensions. If you think about it for a second, this will be tensoring with this guy, and we call this S1. And then lastly we have pi 0 left adjoint, pi 0 shifted by 1 left adjoint, which is tensoring with K identity K, shifted by -1. And this guy we call S2. So the A2 quiver doesn't have a third vertex, but there's a third symbol, if you want. In fact, these three objects are exactly the three indecomposables over the A2 quiver. So I will now construct an autoequivalence of this A2 quiver category, which commutes these three simple objects, and which helps us then to prove that the sheaf doesn't depend on this, on the choice of orientation. So construct U from functors delta 1 d perf. Okay, functors delta 1 d perf. Okay. Autoequivalence commuting DSIs. SIs with shift. And the construction goes as follows, and this really needs Hahn extensions to kind of do reasonable. I mean, you can also you can do this in a DG categorical language or in a triangular language, but this is somehow the right. If you're doing an infinity category, you need Hahn extensions. Is the question?
But this thing that happened before, what happened that we're tensoring with the irreducible things, this will happen in general, right? Because there are too many irreducibles and like
yeah, that's only for anything.
Okay, so it happens really.
Yeah, the convenient case.
But always be tensoring with some subset of the.
Yeah, with the simples and another one, which is the linear, with the one we always have all case.
Ah, okay, yeah.
So we define E1 is the category of diagrams of the following form. X0, xn minus, is it n minus 2 now? Always, right? Yes. Yeah, okay, in my notes it's always n minus 1, so in this way, in the case n is equal to 3. Yeah. Right, no, yeah, okay, perfect. This is inside of functors from delta 2, delta 0, delta 1, d perfect. So, the dots is a bit I'm sorry. The same construction works for any n, and it's better to say just for n is equal to 3 and refer to the vector nodes in the general case. Right, so what is the shape of this diagram? You have a 2 simplex here, and you have a 1 simplex here, and they're glued along delta 0. And in simplicial land, we call this the colimit. And the condition is that these two objects are arbitrary, but these two objects are zeros. This is a category I just defined for you. Why is not clear at this point? Can you define another category for your question?
Trust the comment. So
Yeah?
is this first category the category of diagrams of that shape, such that those top two
Yes.
have the property that they
Yes. Exactly. And the second category is defined as follows. You have y0 goes to y1, goes to 0, goes to 0, goes to x1, goes to x1. This was an x0. And you require that both squares are bicartesian. And this lives inside of functors from delta 2 times delta 1 to d perfect k. And yeah, it's just a full subcategory of diagrams which have these properties of being bicartesian and there being zeros where as indicated. And then you have restriction. They define your functors from E2, R2, E1, R1 to functors from delta 1 to d perfect k. And now we use this magical fact of left-hand extension being fully faithful. So this functor here is in fact, so left-hand extension from functors from delta 1 to the curve of k to functors from delta 2, delta 0, delta 1 to curve of k. This is it left-hand extension? Yes. Has image E1. So what does this mean? Such a diagram is the left-hand extension of its restriction to this part. Why is that? Because if you look at this pointwise formula for Khan extensions, you have, if you call these objects 0, 1, 2, let's call them star and subframe. If I compute this relative over category, delta 1 over star, I think it's under star. Yes. Should I have been under at this over there? No. No, it's over. It's over. Thank you. Yeah, it's over star. So this is actually empty. There are no maps from either 1 or 2 to star. Thus, somehow the left-hand extension evaluated at star is the colimit over the empty set, which is 0. So somehow the condition of putting here 0 and here 0 means that your diagram is the left-hand extension of its restriction to this part. Hence, R1 is exactly the inverse of left-hand extension. Fully faithful functor, this is the image, meaning it's an equivalence on the image, and then this is invertible. So this is an equivalence of categories. Kind of magical, if you see it the first time. And then R2, well, R2 is actually a right-hand extension inverse. Right? If you take such a diagram like here, once you're computing the limit, this is computing the pullback here, which means the square will be a pullback square, hence bicartesian. And same here, you'll get a pullback square, and this is bicartesian. So diagrams in E2 are the right-hand extension of the diagram of the diagrams in E1. So this is also an equivalence. And we can now define a functor define U from functors delta 1 to d puff, okay, to itself by you take functors delta 1 d puff, okay, you take the two restriction functors, you take their inverses, this brings you to e2, and then you restrict to y0 goes to y1. And this lands you again in functors from delta 1 to d puff. Okay. And by construction, this functor is an equivalence of categories. So this is an equivalence of categories, and a dual argument will prove that this is an equivalence of categories. Hence, this is an autoequivalence. And yeah, comes out of concept. Yeah, please.
Can we use using left-hand extensions as like a way to say that 5 is a contractible? Like, when you forget this information, I want to say you're not actually forgetting information.
Yeah, you kind of, the idea is that you're always free to adjoin zeros from map from zeros, because a map from a zero is somehow, it's empty information. It's a contractible information. Hence, you're not adding anything to your category by saying there's a morphism from zero. And similarly, by completing two pullback squares, you're also not adding any information to your category. And this is why it's an equivalence of categories. That's the conceptual rule.
And left-hand extensions are a way like actually they have to solve.
Right, exactly. And they're not even that complicated. You can pointwise formulas. This is something in practice when you work with infinity categories, you do all the time. Whenever you want to build an infinity functor, half the time I would say you use Cunning extension. The other half you cite in the paper. You'd probably use Cunning extension. So now let's compute. Let's do computation. So we start with S0. This is S0. Now we want to compute u of S0. So we add the zeros, and then we compute the pullbacks. We get here k, and here 0 goes to k. Right, this is an equivalence. The pullback along an equivalence with 0 is 0. And this is u of S0, which is equivalent to S1. Kind of easy. Okay, next computation. We start with S1. And we do the same thing. So we add zeros, this is easy, and now we have to compute a pullback. Now it's a non-trivial pullback. We have to remember that this pullback is the -1 shift, which we learned on the preparatory lectures. So this is pullback, and then the next pullback is, these are all zeros, so this pullback here will be just the identity, k -1. So this is saying that u of S1 is equal to S2 shifted by -1. And then let's compute the last pullback. We start with S2. And we compute here, the pullback here again is 0, and here we get k -1. So u of S2 will be S0 shifted by -1. And so, let me squeeze this here. Lemma fb of b to the I composed with u will be equivalent to f v goes to e I -1, or f goes to e from v goes to e2 shifted by 2. This is for I is equal to 3. This is for I is equal to 1. So with this lemma is gives you the rotation invariance of the gentle sheaf. So the way you have to understand this rotation invariance is that so a rotation is now this action of u. By the way, u is the stair functor, if you know what that is, but let's not worry about it. So u is the stair functor. So decompose with this. And then what happens on our sheaf is that all the maps get rotated, except that one gets a shift by 2. You cannot get rid of the shift by 2, it's just 5. But this means that as a sheaf, the category of sheaves as far as the functor category out of the exit path category. In this functor category, this is equivalent. The same way as, say, this is not, it's not a natural equivalence. It's in the same way that if you have a functor from A to B, then you have A prime, E prime, and you have F prime. What's an equivalence of such diagrams? It's an equivalence here, which is U, and an equivalence here, which would be shift by 2. And then kind of, it's an equivalence in this sense. And the way you prove this lemma is simply by proof. You pass to left adjoints.
You have 6 blackboards. Yeah, very small.
Okay, right. Yeah, I want to keep the CAN extension blackboards because CAN extension keeps happening during the talk. So I have 4 blackboards. Let me erase the other 2. Yeah, the proof is pass to left.
I started too early.
No, it's true. Now you pass to left adjoints and then you use this computation. In the other functors, they are given by tensoring with the simple, and the simple is rotated by the U functor. And yeah, this is kind of what you have to compute.
Because U is a surf functor or a sheaf, right?
Good question.
So I think it's actually tau.
It's tau. Okay. Tau is step functor shifted by -1 or +1? -1, okay.
Now it's here when you shift this one, -1.
All right. It's close to the step functor. Let's say like this. It's also a bit beside the point. You can define this functor without having to know what a step functor is. Okay, let me give you the definition of a gentle sheaf in general. So, definition. We call f from exit of G to stable a gentle sheaf if for all n-valent vertices V of G with corresponding inclusion. So if you take an n-valent vertex, the n spider is somehow a subgraph of your ribbon graph, and you get a fully faithful inclusion of the exit category. This is fully faithful. We have that f restricted to exit of Gn. This is equivalent to Fv inside of this functor category. So in this sense, being a gentle sheaf is a local condition. Your sheaf is gentle if on every n spider it's gentle, and then that turns out to be good definition. Let's do some examples. First example, the surface S will be the foreground, and our graph will be this graph. It's a trivalent graph. Then let's draw a gentle sheaf. D perf of k. This goes to pi1. D perf. Should have introduced coordinate notation for D perf. This takes a long time to write. Yeah, the typical trick is to work with large categories, but then we didn't have time to talk about presentable infinity categories, so I'm stuck with D perf.
So far, anything you said would be true for just a small state category.
Well, D of k is not small. Yeah, D perf is small. Okay, so almost there. So this is such a diagram is a gentle sheaf on the foreground. If you now compute the limit, what you get? Well, you get the gentle algebra of the foreground, which is the A3 quarter. Limit is equivalent to the derived category of A3. Anyway. Now, there's an interesting fact, namely, any two gentle sheaves on this ribbon graph are equivalent. And I'll post this as an exercise for you. Exercise. Any two. Say again?
The limit is a small category, right?
Yeah, perfect. I said in the beginning, all derived categories are perfect. Okay. Any two gentle sheaves on T are equivalent. This is only true for this specific ribbon graph. And basically the way you prove this is choose a different gentle graph, a gentle sheaf. Then you can rotate both triangles, such that it looks like this, up to shifts. And then you remove all the shift functors. So kind of, yeah, that's how you prove it. But I'll leave the exercise to you. Now we have a second example where this is not true. So this example is on the back. Let's take the annulus. Marked surface with two marked points. Let me follow my points. And let us choose a number. Then a gentle sheaf. How would it look like? We would have here functors from delta 1 to d puff. Okay, we would have here d puff. Okay, going with pi 0, fiber, pi n, and now we are free to put here shift by n. This goes to d puff. Okay. D puff. Okay, here you put again functors. Pi 0, pi 1, and now it's a fact that every gentle sheaf is equivalent to such a diagram. But such a diagram depends on an integer n. And the problem is here, why can you not do the same trick of rotating and then removing shifts? Because there's a circle, and you will never be able to get with an equivalence the shift out of the circle. So somehow the non-trivial homotopy type of the graph means that your gentle sheaves are not necessarily equivalent. So, in fact, those different sheaves for different n and any gentle sheaf equivalent to the above. Equivalent to above. And so what is the meaning of this number? The meaning, so this has to do with gradings of the surface, a topic which we won't have time to discuss properly. So the surface S has a grading, or what is a grading? Is a line field. And the line field is determined by its winding numbers. By its winding numbers, which are inside of Z. And if you're on the annulus, the line field is determined by a unique winding number, which is the winding number along the loop, which goes around the middle. And so this winding number is the shift by n. And so there's a general result.
The global sections in this case, because they're quite easy to describe, right?
Oh, yeah, exactly. I'll say that in a second.
Okay.
And the global sections will be always the same.
Always the same? No, they will be different. So your topological Fukaya category will depend on not only the surface, but a choice of line field for the surface. And I don't want to go into this so much, it's kind of a technical topic. And it will be a bit beside the point of the techniques we want to illustrate in this lecture series to really spell this out. But yeah, kind of roughly speaking, it's an additional data you put in your surface, and your topological Fukaya category depends on this. And in terms of the gentle algebras, the meaning is the grading of the gentle algebra. If you change the degrees of the arrows in the gentle algebra, this means you're changing the grading of the surface. And yeah, you can kind of work all of this out very precisely.
Maybe as an example, if you think of the Kronecker curve,
Yes.
if you put a grading that's not very close, they're not both arrows have the same grading, you cannot grade the bands. So all the bands that you would actually expect to see, you cannot grade, so all the band modules vanish. So it's no longer equivalent.
So in this example, for the endless example, the global sections is equivalent to the representation of the Kronecker curve, where, and now, yeah, maybe I should have prepared that. So one of them will be in degree 0, and one will be in degree n. And is it the same n as there? Is it minus n? Is it n plus 1? I don't know.
Maybe it's minus 1. So yeah, okay.
Well,
A function of it.
it depends linearly on n. It depends linearly on n. Affine linearly. Yeah. Okay. Yeah. So this is that. And of course, like you can always grade the second vertex to make the lower arrow to be in degree 0, and then the possible gradings on the Kronecker curve are just the integers. If I say my lower arrow is degree 0, then the upper one is degree n. If I have this, it should be in degree b, then I can shift this one, and then this becomes n minus b. So this is somehow, this all matches very nicely. And let me end, then, well, we didn't get to contractions of ribbon grass. Maybe we'll have to continue with that in the next lecture, and then get to macro gluing after that. So the result is that there's a bijection between equivalence classes of gentle sheaves on G, where G inside of S is spanning, and line fields slash gradings. Talk is too small. Gradings of the surface, and if you want to learn more about this bijection, you can go to the lecture notes, and there's more hints with references to papers where things are worked out. So it's a long story to make this bijection precise. I think in the annulus case and the disk case, we're kind of appreciating what's behind this bijection. Okay, maybe this is a good point to stop then. Thanks for listening. Yeah, ask.
So you kind of hinted that these constructible sheaves are the compact objects in some large category.
No, what I mean is that we're taking values in stable categories, small stable infinity categories, and you could do the same machine with large stable infinity categories.
Yeah.
Where you take unbounded derived infinity categories here, and which one prefers is to some extent preference.
But would this then be the compact objects in what we get in the bigger?
This is a non-trivial question in general, and the answer is somewhat subtle. So this depends on the marked surface. We're working in this context where every boundary component has a marked point. Symplectically means every boundary component has a stop, and in that setting, that result is true. This is because they will be smooth and proper. If you remove this assumption, then there will be two different versions of the Fukaya category. One will be smooth, one will be proper, and they will not be the same. And this result just mentioned is basically not true anymore because this fails.
And what do the large categories form as 6 forms of formalism on some?
I'm not sure. Yeah?
Could you just say like how to get the store contours or the two values of the contour from this picture, how you get those values?
Yeah, so the way you compute this is with, so first of all, to compute the limit of this diagram, we can remove this thing, and in this thing. They do not contribute to the limit. Perfect. Next, I use the color. And so you have, this is this quiver with two vertices, 2 and 1. So how do you compute such a limit? You pass the adjoint diagram and compute the co-limit. This is how you do it in practice. So, and to compute this co-limit comes from a diagram of quivers. So this will be 1, this will be 1, and they include here and here, and this will be, sorry, this will be 2. And this is the same 1 plus 2. You have the same inclusion here. And you're then computing this co-limit of infinity categories as the derived category of the co-limit of the quivers. In the co-limit quiver, in this case, it's just the conical quiver. It's somehow 1, 2. And this is how you compute these gentle algebras. This is also what Jan explains more in his talk. The gentle algebras are glued together from AN quivers. And if we had time to talk about homotopy co-limits, we could kind of unravel all of this and make it precise and show that these are always gentle algebras, and this is kind of the idea of where they come from.
What you told us yesterday about computing using this Cartesian sections of the Grothendieck construction, we can see now that this consists of 2 maps whose source and target agree up to a sheaf.
Yes. As well. So
this heuristic and the object.
yeah, so let's say instead of fiber, we have here pi 1, pi 0. We're free to rotate, right? Our graph, right? And then you have AB gets mapped to A, gets mapped to B. And so you're basically saying I have 2 vector spaces, A and B, a linear map between them, and another linear map between them. So using coCartesian sections, you can, I mean, you can't prove this equivalence so easily, at least, but you can appreciate it. Other questions?
Just one, like that co-limit argument, is this just saying that like functors to the k, it's like terms co-limits and all that? Like can one literally say that?
Yes, there's such a result that if you have a diagram of say quivers considered as DG categories with finitely many objects, then the homotopy co-limit of this diagram, this is another DG category, its derived infinity category will be the push co-limit of the corresponding diagram of derived categories of these DG categories. And everything here is cofibrant, so if you're computing the homotopy co-limits, you're just computing strict co-limits. And we didn't talk about this in lecture course. This is for experts.
Could you push out the orbs?
Any more questions? So let's thank Merlin again.